Hello, in this video we're going to derive the mean and the variance of a t-distribution, and here is the density of a t-distribution. It's over the real number line, and we have integer degrees of freedom that are, the counting numbers, 1, 2, 3, etc. Let's first show that it's a PDF, and then before we derive the mean and the variance. So to show it's a PDF, we need to integrate it over its domain, show that it equals 1. And so we, one note here, note that it's t squared, and that's the only variable in here. So it is an even function. It's symmetric about 0. So we can just integrate half of it and then multiply it by 2, and that's the same. And that's a quick justification. You can actually split this into 2 intervals, do a variable change, and show that they're equal, then just combine them, take them times 2, but I'm going to skip it. So here, once we're here, let's do a variable change of x equals t squared over r. This here, you can back solve for t. The dx is 2t over r dt. So we plug those in. So our constants stay the same. We put in x for right there, and then dx is this, and the r is because when we multiply it up and divide down, then we also have to put in t, but t is r times x to the 1/2. And so this r cancels with one of those r's. That's how we get the square root of r. So now we do some simplifications. This 2 cancels with this 2. This radical r cancels with this radical r. And we take this to the top. So when we take it to the top, it becomes negative 1/2. But we can call it x to the 1/2 minus 1, and then here we can break that up into 2, so it's 1/2 plus r over 2. That's the same here, and we have basically the constants here. And then technically we're done because we're integrating from 0 to infinity, and this is a beta function. So now it's one of the forms of the beta functions. It's actually not as well known, and so instead of stopping here, I'll transform it to the beta distribution that we generally know. But normally we could go done, it integrates to 1. So now let's let x equal y over 1 minus y. Take the derivatives of each side. We can even take this and solve for 1 plus x. We do this so we can substitute in here, and this x will go here. So now we substitute in, and we plug in there. 1 plus x is this, and dx is this. Okay, so now we simplify. So we can take everything up and break this apart, and we end up with this. That's algebra. I'll let you do it. We end up with y to the 1/2 minus 1, 1 minus y to the r divided by 2 minus 1. And this is the typical beta function that we know. So then we have gamma of alpha, gamma of r over 2, and then when you add those two together, you get gamma of r plus 1, and that does integrate to 1. Now we're going to make use of this form in part of our derivation. And so here, this is alpha, and that's beta. And so when we're going to come back to that. So let's look at the mean. So the mean of t is you plug in t and take it times its density. Now let's let x be this piece in the parentheses, and then you can take the derivative here and plug these back in here, and you get this. Okay, things cancel out. So this is, you just get x, but this t is part of this t, and they cancel, and you end up with this. Okay, so you have constants out front. Now, notice I didn't put the limits of integration because we're going to bring it back to the t world in a second here. So now when you take the antiderivative of this, you add 1 to it, divide by that, and then take it times its limits of integration. So you get, x. But we're going to replace x with what we said so we can bring it back to the t world, and we know the limits of integration here. So now if you, this is a constant in regards to t, so it can factor out. And then this is a negative, so it can, I think of it as coming down. So when you plug in infinity, this blows up to infinity, which makes this whole thing go to infinity. But remember, we're in the denominator because that's a negative, and then that goes to 0. And the same thing when you plug in a minus infinity here, this limits to 0, regardless of what these constants are. So the mean of a t distribution is 0. Now, one detail that we skipped over is that one of these tails has to be finite, or we have to make sure. So when we take the limit of, say, the top half of this from 0 to a, and then let a go to infinity, and it's a constant times this junk here, which is this. We need to make sure that it goes to is finite. So now when we take the antiderivative of this, we got this, but then that comes out as another constant called c prime. So we're taking the limit as a goes infinity of this from 0 to that. We plug in 0 and a, and we get this. And then the limit of this is finite. It does, as a goes to infinity, this is not infinite, so it is finite, and this is for r is greater than 1. So the second moment, we take t squared, plug it in with our density. We can break it up into 2, and if we do a variable change here, then it ends up equaling this piece again, so we can just take 2 times it, because this is an even function, so we get this. So now we plug in our numbers and we get this. So we got the x squared and then times the density. We got a lot of constants out front. We take y, we let y equal this piece here. Then we take the derivatives, and we can back solve for x squared because that's what this is. Then we plug in our numbers here. We have our constants, but when we plug them in, certain things cancel. The 2 cancels. This becomes r, and we get this. So now let's take this to the top, add it with this y, bring out the r. That's what this is. Now make this look like a beta. So this is the alpha minus 1. Then we have alpha plus beta. So this is a beta distribution. And so it integrates to, this. If we were to take the reciprocal of this and put it in here, then it integrates to 1. But since we don't have it, then it integrates to this piece. We could take the reciprocal, stick it in there, and it integrates to 1. It's not there, we get this. Now when you do all the simplifications, this is 1/2 times gamma 1/2, so the gamma 1/2s cancel. Things cancel out, and we get r times 1/2 divided by r minus 2 over 2. Simplify this, we get r divided by r minus 2. And this is only valid for when r is greater than 2. Some of these integrals don't converge unless that's the case. Then the variance is x squared minus the mean, but the mean was 0, so it's just the expected value of x squared, which we determined was r divided by r minus 2, and this is valid for r greater than 2. Well, that's all I have for this video. If you enjoyed it, please like it and subscribe so you don't miss the next one. Thanks. Bye.